Welcome to our second thermodynamics video. I have yet to make the first one, but you experienced that in class, so technically this is our second lecture. All right, let's talk about the universe. Entropy of the universe, delta S universe, and thermodynamically favorable. So we're going to be relating things using entropy and if they are going to be favorable or not, or spontaneous or not. The universe is made up of a system and its surroundings. So for instance, if my system is a beaker full of water, and I'm looking at how temperature is changing within this beaker, and maybe it's releasing heat, so the system is releasing heat into my surroundings, the universe encompasses both my system and my surroundings. So you could then say that the entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. So it's basically just saying the change in entropy of the universe is everything, all of the entropies added together. If the change in entropy of the universe is greater than 0, then the reaction is thermodynamically favored, or you could say it's spontaneous. As we stated earlier, the speed at which the reaction occurs does not matter. It does not have to be fast to be spontaneous. Now, if the delta S of the universe is less than 0, the reaction won't happen. The heat flow links the system to the surroundings. So if heat is leaving the system, then heat is entering the surroundings. And you could call this an exothermic reaction. And you could say, well, since the heat is leaving the system, then the surroundings are gaining energy, they're gaining heat, which is probably making them more chaotic, which is increasing the entropy. So the surroundings would have a positive change in entropy. However, in an endothermic reaction, the surroundings are sending heat into the system. They're losing some of that energy, and so the particles of the surroundings might be slowing down and maybe becoming a little more orderly. Boo, boring. And their entropy would be less than 0. So let's talk about Gibbs free energy. This is really how you figure out if something is going to be thermodynamically favorable. So remember, in class we mentioned that this degree symbol in this unit actually means standard conditions. And we're not saying STP, that's different. Standard conditions are talking about the average room. The average room is at 25 degrees Celsius or 298 Kelvin and 1 atmosphere. So delta G stands for Gibbs free energy. This is Gibbs free energy at standard conditions is equal to the change in enthalpy at standard conditions minus the temperature in Kelvin times the change in entropy at standard conditions. And by looking at the sign of the Gibbs free energy, you can figure out if something will be thermodynamically favorable. If the change in Gibbs free energy is greater than 0, so positive, then the reaction is not thermodynamically favorable, non-spontaneous. If it is negative, then the reaction is thermodynamically favorable. So let's think about that. If it is negative, that means that the chunk with the entropy is really large compared to the chunk with the enthalpy. So that would make sense. If it has really high entropy, then it's going to be favorable because the universe likes disorder. However, if we have a really large enthalpy and not very much entropy, then it's not going to be favored because the universe wants there to be a lot of entropy. Now, if delta G is equal to 0, then the reaction is not thermodynamically favorable, so this is not a less than or equal to situation. If it is equal to, then it's not favorable, and it's also at equilibrium. Phase changes, so like liquids converting to gases or solids converting to liquids, and in the reverse, they are at equilibrium, so the delta G is 0. So if you ever have a problem that is asking you about the thermodynamic favorability of a phase change, you could just say, oh, I know that the delta G is 0, so it's not thermodynamically favorable. And again, temperature must always be in Kelvin. So flashback here, exothermic reactions, this has to do with releasing energy, releasing heat. Those have a negative change in enthalpy, whereas endothermic, which is absorbing, those have a positive delta H. Ooh, pot. Huh. Interesting. Positive. Reactions that release energy tend to be thermodynamically favored. So exothermic reactions, these guys, tend to be spontaneous. TFP, thermodynamically favored process. Yes, that's it, TFP. And then endothermic reactions, not so much. Then you could say reactions that become more random also tend to be thermodynamically favored. So if you have a negative delta H or a positive delta S, it's more likely that it'll be thermodynamically favored. So let's go through some thought problems. Imagine if the entropy increases and the reaction is exothermic, will the reaction be thermodynamically favored? So if you get a question like this, what you want to do is figure out the signs of delta H and delta S. If entropy is increasing, that means your delta S is positive. And if it is exothermic, your delta H is negative. So here's your Gibbs free energy equation, and we're plugging in our negatives and our positives. So let's see. If the entropy is positive and you are subtracting it, and the enthalpy is negative, so you'd end up with a negative number minus a positive number. Well, if you're doing that, you're going to end up with a number that is always negative. Here, let's see, it's like this, negative x minus a positive x. So this will always come out negative, which means that you will always have a thermodynamically favored process if the enthalpy is negative and the entropy is positive. So you'd want to be able to think of these in this manner. You'd want to be able to identify what would be negative, what would be positive, and will it always be favored, or does it depend on something? Let's try this one. If the entropy increases, so you tell me if the entropy increases, is that positive or negative? It's positive, which you could have figured out by looking down there, but whatever. And then if it's endothermic, we know endothermic reactions have a positive change in enthalpy. So let's try plugging those in. If the delta H is positive, you have a positive number minus another positive number. Can we always say that it will be coming out as a negative number? Will it always be negative? No, not always. Because what if we have a really, really low temperature? That'll make this whole number very small, which will make the enthalpy overpower the change in entropy, which would make the delta G positive. So what you'd want to be able to say is, at higher temperatures, then that will make this entropy chunk larger, which will make the negative chunk larger, which will allow it to overpower the positive enthalpy chunk, and the reaction then will be thermodynamically favored. So this one depends. It depends on the temperature. If they're both positive. And we have a summary slide later, so if you don't write that down, it's fine. We'll get there. Okay, if the entropy decreases, so the delta S is what? Negative. And the reaction is exothermic, so delta H is what? Also negative. So will it be thermodynamically favored? Plug in the signs. If I have a negative delta H as well as a negative delta S, well, again, this one's going to depend on which one is larger. Because if I plug in my negative delta S, that turns this into a plus sign over here. A negative times a negative. And then it just depends on how large this chunk is compared to the negative delta H. If your temperature is really small, then the negative delta H will prevail and you will have a negative Gibbs free energy, and it will end up, actually I probably shouldn't write that, I'll just leave it out, and then you will end up with something that's thermodynamically favorable. So at low temperatures, the entropy will be smaller, that chunk will matter less, and the delta G will be negative. So this one, again, it depends on temperature. Whoa. Temperature, if both are negative, okay, one more thought problem. If the entropy decreases, that's a delta S that is what? Negative. And the reaction is endothermic, so delta H is what? Positive. Will the reaction be thermodynamically favored? So let's plug those in. We have a positive number minus a negative number. Minus a negative. These both become positive then. So now you have two positive numbers added together, which means your delta G must be positive. And if your delta G is positive, the reaction will never be thermodynamically favored. So if you have one positive, one negative, where the positive one is enthalpy and the negative one is entropy, you know it will never be favored. So in other words, endothermic plus a decrease in entropy is non-thermodynamically favored. So let's summarize these ideas. Woo, that's a lot. All right, so if you have a negative delta H and a positive entropy, you know it will always be negative, so it's always spontaneous. If they're both negative, then it kind of depends. It must have a low temperature in order to be spontaneous. But if it has a high temperature, it will be non-spontaneous. If they're both positive, again, it depends. If you have a low temperature this time, it's non-spontaneous. But if you have a high temperature, it will be spontaneous. And then finally, if your enthalpy is positive but your entropy is negative, then it will never be spontaneous. I wouldn't necessarily recommend memorizing the chart. I'd recommend just plugging in fake numbers. Unless you're really good at memorizing, then you could do that. That's fine. All right, that's the end of our second video.